Today we will learn the UML, Unified Modeling Language. It is a language for documenting models, became an ISO standard in 2004, and it has some syntax, that is a set of basic symbols and sentence formulation rules, and there are some semantics, meanings of some basic symbols and sentences. The UML actually is a language for documenting models. As in case of other language, UML has its syntax and semantics, and it provides a set of basic graphical notation. For example, rectangles, lines, ellipse, etc. that can be combined in certain ways to document the design and analysis result. It is important to remember that UML is neither a system design nor a development methodology by itself, nor it is tied to any specific methodology. It is an independent of any specific design methodology. It is used to document object-oriented analysis and design results. UML can be used to document object-oriented analysis and design results that have been obtained using any methodology. It is merely before the design methodology. It is not only the prescribed entire different design steps, but each was tied to some specific design modeling language. It can be used to document object-oriented analysis, and design results have been obtained using any methodology. Now, the origin of UML. In late 80s and early 90s, there was a object-oriented design technique and notation. There was some object-oriented design techniques and notation. Many of these had become extremely popular and were widely used, but the notations they used and specific design paradigms at that time it is used they were different from each other in major ways. But there are so many popular techniques to choose from, and it was not very uncommon to find the different project teams in the same organization using different methodology and documenting their object-oriented analysis, design results, using different notations, etc. etc. So there was a problem. So these diverse notation used for documenting design solutions and gave rise to a lot of confusion among the team members and made it extremely difficult to reuse or to understand or to communicate each other of the project members. So that's why the UML has been developed to standardize the large number of object-oriented modeling notation that existed in early 90s. So the different software development houses were used different notations, methodologies were tied to notations, and UML developed in early 90s to standardize the large number of object-oriented modeling notations that existed. So the UML was developed based on some standard large number of object-oriented modeling notations, and the principles are taken only from OMT that was developed by Rambach in 1991, the Booch method that was developed by Booch in 1991, the OOS Jacobs in 1992, the Odles method, Schaller and Miller methods. Actually, these different types of methods are combined into the UML. These different object-oriented techniques are used, are combined into a single model that is called UML. UML has borrowed many concepts from these modeling techniques, and the concepts and notations from especially the first three methodology have heavily been drawn up. The first three, that is OMT, Booch, and OOSP. The concepts and notations from especially the first three have been drawn upon, and as shown in figure, you can understand that UML has adapted by object management group And as acting object management group is not a standard formulation body, but in association of industries that tries to facilitate early formulation of the standard, object management group aims to promote consensus notation and techniques with the hope that if the usage becomes widespread, then they will automatically become the standard. So the first object-oriented management group prepares this UML, and then widespread use of UML has been done, and then the UML has become standard in near about 2005, 3 years in that time. UML is now being used in academic and research institutions as well as in large number of software development projects worldwide. Obviously, interesting. Uh, it is interesting to note that the use of UML is not restricted to the software industry alone. And as example of UML's use outside of software development problems, some car manufacturers are also planning to use UML for their build to order initiative. And we can draw these UML or case tools in rational rows, or we will use in lab in some Argo UML to draw this UML diagram. Okay, so object management group is an association of industries. They promote concepts, notation, and techniques. UML also been used outside of the development areas, as we have car management. The evolution of UML. Since its release, the UML in 1997, the version of UML was 1.0, and it continues to evolve with feedback from practitioners and academicians to make it applicable to different system development situations. Almost every year, several new release. Several new release of on this one UML 1.0 were announced, and here we have shown it in UML 1.8. Okay, but a major change has been done in 2003, and the name was UML 2.0, or sometimes it is said in 2007. Since the use of embedded application is increasing rapidly, so there was a popular demand to extend UML to support the special concepts and notations. UML 2 actually was an attempt to make UML applicable to the development of concurrent and embedded system actually. For this, the many new features such as events, ports, and frames in sequence diagrams was also introduced. We briefly discuss this development. We will briefly discuss this development in next. And before we discuss the features of UML in detail, it is important to understand that what is model. A model actually is an abstraction of a real problem or situation, and is constructed by leaving out unnecessary details. So in the model, it will reduce the problem complexity and makes it easy to understand the problem or the situation. It is a simplified version of a real system, and useful to think of a model as capturing aspects important for some application while omitting the rest one. And the size of problem, as the size of problem increases, the complexity also increases exponentially due to human cognitive limitation. Human cognitive limitation means, suppose I am giving you a number, suppose 5,000, to keep in mind. So it is easy to you that 5,000 to remember. But if I change this 5,000 number into a binary number of code and say that you please keep in mind, then it is a very complex situation to you that you can remind this number into your mind. So this is human cognitive limitation. There is a limitation of human that he can store in his memory, short-term memory, a digit of 7 to 10 numbers. So therefore, to develop a good understanding of any problem, so it is very much necessary to construct a model of the problem. Because when we modeling the problem, the complexity will be distributed into different modules, and these modules are turned on very easily understandable things. And that's why we use a model, and it is very essential tool in software design and helps to effectively handle the complexity in a problem. So these models that are first constructed are the models of the problem. So first we have to construct the models of the problem. Then a design methodology essentially transform these analysis of models into some design perspective, uh, into some software code or anything other. So different types of models are based on specific aspects, are obtained based on specific aspects of the actual system that are ignored while constructing the model. To understand this, consider an architect of a large building, the construction of a large building. While the constructing the frontal view of a large building, the architect ignores the aspects such as floor plan. They will not show into their plan. The strength of the walls, these details will not be available into the frontal view. The details of inside architecture also is not available into the frontal view, etc. So when we are going to construct a specific aspect, the actual system, then we should ignore the construction of the other system. So while constructing the floor plan, the completely ignore the frontal view, side plan, thermal and lighting characteristics, etc. of the building. A model in the context of software development can be graphical, textual, mathematical, or program code based. Model may be graphical, may be textual, may be mathematical, or program code based. The graphical models are very popular because they are easy to understand and construct. The UML is primarily a graphical modeling tool. UML is a graphical modeling tool. So, however, there are certain modeling situations for which, in addition, the graphical UML models, the separate textual expressions are required to accompany with the graphical model. So, the graphical model singly is not exist. Some textual models, some textual lines also added into these graphical models, and then we can get this UML diagram. In this section, we here in the UML diagrams can capture the 5 views of the model. UML1, UML2 can be used to construct of 9 different types of diagrams, but here the 5 different views of the system. 5 different views of the system. Just for modeling of several views such as ventilation perspective, electrical perspective, lighting perspective, heating perspective, etc. So these are the different views. The different UML diagrams provide different perspective of a software system to be developed and the facility of comprehensive understanding of the system. If a single model is made to capture all these required perspectives, then it would be a complex as well as original problem and would be little used. That's why we divide these views into different structures. So first view is user's view, then structural view, then behavioral view, then implementation view, then environmental view. Once a system has been modeled from all the required perspectives, the construction model can be refined to get the actual implementation of the system. So once a system has been modeled from all the required perspectives, then the constructed model can be refined to get actual implementation of the system. So we should observe here that the diagrams can be refined to get the actual implementation of the system, and diagrams are used to realize the important views of the discuss. We first provide a brief overview of the different views here, and here we can see that this diagram of important views supported by different types of diagrams in UML. and the user's view captures the view of the system in terms of functionalities offered by the system to its users. So first is the structural view. The structural model is also called the static model, and since the structure of a system does not change with time, the structural view actually defines the structure of the problem or the solution in terms of the kinds of objects, that is classes, important of the understanding of the working of the system and to its implementation. It also captures the relationship among the classes or objects. So structural view defines the structure of the problem, that is the relationship of classes or objects between them. Then the behavioral view. The behavioral view actually captures how the objects will interact with each other in time to realize the system behavior. So these are the diagrams, sequence diagrams, collaboration diagrams, state chart diagram, activity diagram. These diagrams helps to find out the behavioral view of a system. The system behavior captures the time-dependent behavior of the system, and it therefore constitutes the dynamic model of the system. The next one is implementation view. This view actually captures the important components of the system and their independencies. For example, the implementation view might show the GUI part, the middleware, and the database part as the different parts, and also would capture their interdependence. Okay, so this is the implementation view, which is important, which captures the important components of the system and their interdependence. So last one is environmental view. This view actually models how the different components are implemented on different pieces of hardware. How the different components are implemented on different pieces of hardware. Okay, so for any given problem, should one construct all the views using the diagram provided by the UML? The answer is no. For a simple system, the use case model, class diagram, and one of the interaction diagram may be sufficient. For a system in which the objects undergo many state changes, then a state chart diagram may be necessary. For a system which is implemented on a large number of hardware components, then a deployment diagram may be necessary. So the type of the models to be constructed depending on the problem. Okay. So and then we will discuss the class diagram. Actually, class diagram is a set of classes and their relationships. In object diagram, it shows the set of objects, that is, and their instances, that is the class instances and their relationships. In component diagram, the logical grouping of elements of their relationships are stored, are viewed, and in deployment diagram, the set of computational resources that host each component are to be deployed in the deployment diagram. In the use case diagram, the high-level behavior of the system, that is user's goal, the external entities, actors, these are viewed in the use case diagram. In the sequence diagram, it focuses on time ordering of the messages. So the time, that means how much time is necessary to move this message from one position to another position, when the acknowledgement will be received. These are which one comes after which one. Then this is showed into the sequence diagram. Then the collaborative diagram, which focuses on structural organization of objects and messages. Actually, the structural organization of objects and messages, how they collaborate to each other, how they transfer data from one to another, these are shown here in collaboration diagram. The state chart diagram, it event driven the state changes of the system. That is, the system is in which state, the running state, or in working state, or in some pause state, etc. These are shown in state chart diagram. Then the activity diagram, it flows of control between the activities. The activity diagram shows the flows of control between these activities. The use case model consists of a set of use cases. It is a central model, and other models must conform to this model. Not only any object-oriented model, it is a functional model of a system. So, the use case model of any system consists of a set of use cases. Intuitively, we can say that the use case represents the different ways in which a system can be used by the users. The simple way to find the use cases of a system is to ask the question that what all can the different categories of users do by using the system. That means what are the different categories of users who are using the system. So when you can answer these different categories, when you can divide these different categories, then you can easily draw the use case model. For example, in case if a library in a library information system, the use cases could be the issue book, the query book, the return book, the create member, the add book, etc. Roughly, we can say that use cases correspond to high-level functional requirements. Use cases correspond to high-level functional requirements. And we can also say that use cases partition the system behavior into the transactions. We can say that the use cases partition the system behavior into the transactions, such as each transaction performs some useful actions from the user's point of view, and each transaction to complete may involve multiple message exchanges between the user and the system. The purpose of a use case is to define a piece of coherent behavior without revealing the internal structure of the design of the system. So a way in which the system can be used by the users to achieve the specific goals and corresponding to high-level requirements, and it defines some external behavior without revealing the internal structure of the system, and its set of related scenarios tied together by a common goal. So these are the features of use case model. A use case typically involves a sequence of interaction between the user and the system. Even for the same use case, there can be several different sequences of interaction. A use case consists of one mainline sequence and several alternate sequences. The mainline sequence represents the interaction between a user and the system that normally takes place, and the mainline sequence is most frequently occurring sequence in interaction. Okay, a use case can be viewed as a set of related scenarios tied together by a common goal. The mainline sequence and each of the variations are called scenarios or instances of the use case. Each scenario is a single path of user event and system activity. Use cases appear normally independent of each other, and implicit dependencies may exist, but in library automation system, the renewed book and reverse book are independent use cases. Renewed book and reverse book are independent use cases. But in actual implementation of renewed book, a check is made to see if any book has been reversed using reverse book or not. So implicit dependencies may exist in this case. Implicit dependency of renewed book on reverse book. To contrast to all other types of UML diagram, the use case model represents a functional or process model of a system. Normally, each use case is independent to each other, and however, implicit dependencies among use cases may exist between the dependencies as such shared resources, objects, or functions. So in the previous example, in the actual implementation of the renewed book, a check is to be made to see if any book has been reversed by a previous execution of the reversed book of use case. And another example of dependence among use cases is, suppose there is a book automation software and update inventory and sales book are two independent use cases. Update inventory and sales book. But during the execution of sale book, there is an implicit dependency on update inventory. Since when a sufficient quantity is available in the inventory of sales book cannot operate until the inventory is updated by the update inventory. So the sales book can operate only then. That means sales book is dependent on the update inventory. Only then is the update inventory update the stocks. So these use cases models are important analysis and design artifacts. And in contrast to all other type of models of UML diagrams, the use case model represents the functional or process model of a system. Now, the representation of the use cases. A use case model can be documented by drawing a use case diagram and writing an accompanying text elaborating system drawing. In the use of use case diagram, each use case is represented by a ellipse and with the name of the use case written inside the ellipse. So this ellipse is the use case and the name of the use case is written into this ellipse. The use case represented by ellipse. The name of the system being all the ellipses of the system are enclosed with a rectangle which represent the system boundary. So this rectangle, into this rectangle or use case are to be stored, and this is called system boundary. The name of the system is here tic-tac-toe game. The name of the system is here tic-tac-toe game, and backup is one use case and play move is another use case. The name of the system being modeled appears inside the rectangle. The different users of the system are represented by using stick person icon. This is a stick person icon. These are the users. Stick person okay. Each stick person icon is referred as an actor. This is an actor, this is another actor. An actor is a role played by a user with respect to the system users. Okay, so actor is a role played by the user with the system use. It is possible that the same user may play the role of multiple actors. The same user may play the role of multiple users. It is also possible. An actor can participate in one or more use cases, and single actor can participate with one or more use cases. The line connecting an actor and the use case is called communication relationship. This is called communication relationship between actor and use cases. It indicates that an actor makes use of the functionality provided by the use cases. Okay. Both human users and external systems can be represented by stick person icons. Human user and external system can be used as an actor. When a stick person icon represents an external system, it is annotated by this stereotype. Okay, this stereotype means that this is an external system. The stereotype construct, when used to annotate a basic symbol, can give slightly different meaning to the basic symbol. Therefore, eliminating the need to have several symbols whose meaning differs slightly from each other. And here is an example of tic-tac-toe game software, and this software has only one use case, namely play move. Another use case is backup. Note that we did not name the use case get user move or get user move because it would be inappropriate, because these would represent the developer's perspective of the user, okay, of the use case. Get user move is appropriate is not be appropriate because this would represent the developer's perspective of the use case. So in the developer perspective, it is the player and the play move. The move, it will be the play. The use case should be named using the user's perspective. Using the user's perspective, not the developer's perspective. So here are some text description also. That each ellipse in a use case diagram by itself conveys very little information other than giving a healthy idea about the use cases. And every use case diagram should be accompanied by the text description. This is a text description, this is another text description. This should define that the details of the interaction between the user and the computer as well as other relevant aspects of the use case. And it should be include all the behavior associated with the use case in terms of mainline sequence. The various alternate sequence, the system responses associated with the use cases, the exceptional conditions that may occur in the behavior. Also, the behavior description is also often written to the conversational style, but some structuring also is helpful in case of text description, etc. So the external system, by adding a stereotype, we can use the external system. Now, how a connection is an association between an actor and a use case. Between an actor and a use case, there is a connection. It depicts the user's relationship. This is the user's relationship, and connection does not indicate the data flow. This does not mean that the data is going from here to here and here to here. Okay, the connection means only the relationship or association between actors and users. The association relation indicates that the actor and the corresponding use case communication with one another. So this is the association relationship, and it says that the communication, they communicate to each other. Faculty and upgrade grades. The faculty is communicate to upgrade grades. Here is another example of use case diagram of supermarket price scheme description. And here there are customer, sales clerk and managers. Here the customer, sales clerk and manager, and the use cases are register customer, register sales, select winners. So manager will select, will check only the select winners. The sales clerk will only register the sales. The customer will register themselves, and the clerk will approve those registers. Those customers who have registered, they have approved those. So this use case is done by the, and this use case is, will be used by the customer and the clerk both. Factoring, that it is often desirable to factor use cases into components use cases. All use cases need to be factored. In fact, the factoring of use cases are required under two situations. Complex use cases need to factor into simpler use cases. This is the first idea. This would not actually only make the behavior associated with the use case much more comprehensively, but also it will make the corresponding interaction diagram more traceable. Without decomposition, the interaction diagram of the complex use case may become too large to accommodate into a single standard paper. So that's why we are factoring the use cases, so that it does not become too complex, and all the systems, all the use cases can interact with this, or we can view in a single or multiple factors. And the next use cases need to be factored whenever there is common behavior across different use cases. The factoring would make it possible to define such behavior only once and reuse it whenever required. It actually helps to represent the common behavior across different use cases. The three ways of factoring are the generalization, include, and extend. So it is desirable to factor out the common uses such as error handling from a set of use cases. This makes analysis of class design much simpler and elegant. However, a word of caution: keep in mind that the factoring of use cases should not be done except for achieving the above two objects. Only you have to use the factoring when it is a large case or complex case, then you make it the simple use cases. And if it helps, when it helps to represent the common behavior across different use cases. Without these two cases, do not use the factoring. Okay, so the first way is generalization. The use case generalization can be used when you have one use case that is similar to another, but does something slightly different or something more. The child use cases inherit the behavior of the parent use case, and the child may add to or to override some of the behaviors of the parents. So the generalization works in the same way that with use cases as it does in class objects. The child use case inherits the behavior and the meaning of the present use case. The notation is also same. It is important to remember that the base and the derived class are separate use cases and should have separate text descriptions. So keep in mind that base case and derived classes are separate and they should have the separate text descriptions. Then includes it. The include relationship in the older version of the UML was known as the users relationship. The include relationship implies one use case includes the behavior of another use case in its sequence or events and another. That means the includes relationship is appropriate when you have a chunk of behavior that is similar across a number of use cases. It implies one use case includes the behavior of another use case. It is the sequence of events and actions. The factoring of such behavior will help in not repeating the specialization and implementation across different use cases, and it includes the relationships by reusing the factoring out of commonality across the use cases. So here you have to use the stereotype include, and in the include relationship a base use case compulsorily and automatically includes the behavior of the common use case. In this picture, the issue book and renew book include check reservation use case. So it includes the check reservation use case. So when you will issue a book, the base case, this is the base case and this is the common use case. So when the base case may includes the several use cases, in such cases it may interleave their association common use case together. The common use case becomes a separate use case and independent text description should be provided for it. So this check for reservation is included or is used, the same use cases is used in issue book and renewed book in both. That's why we have used this include stereotype here. So the next one is extends. It allows you to show the optional system behavior and optional system behavior is executed only if certain conditions hold. Otherwise, the optional behavior is not executed. The relationship among the use cases is also predefined as a stereotype extends. Okay, so the base case and common case, the extend relationship is similar to like the generalization, but unlike generalization, the extending use case can add additional behavior only at an extension point, only when certain conditions are satisfied. So these are the same, but only here the extends or only certain conditions are satisfied, then the common uses are to be done. The extension points are points within the use case where the variation to the mainline or normal action sequence may occur. The extends relationship is normally used to capture the alternate paths of the scenario. So this three main there are three main ways of this factoring: generalization, includes, and extends. And here is an example of video store information system. It actually supports these following business functions. It records some information about videos and store it on, and then this database is searchable by staff and all customers. So by staff and all customers. So customer is an actor and staff is another actor, and the search for videos is the use cases. So these use cases is associated with this staff and with this customer also. Okay, so the next one is information about a customer's borrowed video. Information about a customer's borrowed video. Information of a customer borrowed video will be by the customer borrowed data. Access by staff and customer. It involves video database searching. Okay, the staff can record video rental and returns by customer. It involves video database searching. This is video database searching. Okay. The staff can maintain customer and video information. Staff can maintain customer. The staff can maintain customer. So staff is the actor and customer is the user use case, and it is also maintained by video information. The managers of the store can generate various reports. Manager can generate reports, and to maintain this video record and return to the videos, we need to search for videos. That's why it is include syntax is done here. So these maintain videos and the return videos are to be search for videos, are the include part of this use case diagram. I think you can understand this use case diagram.